Bonding a subpanel to the neutral bus can create several electrical hazards. Firstly, ground loop formation may occur. Bonding a subpanel to the neutral bus can create a ground loop, allowing stray currents to flow through the neutral conductor instead of the grounding conductor. This can lead to voltage imbalances, overheating, and fire hazards. Secondly, overvoltage conditions may arise. If the neutral conductor in the subpanel is not adequately sized or protected, overloading the subpanel can cause voltage drops in the neutral and overvoltages on the grounded conductors. This can damage equipment connected to the subpanel. Thirdly, electrical shocks are possible. A ground loop can create a path for electrical current to flow from the subpanel enclosure to other conductive surfaces, such as water pipes or nearby metal objects. This can result in dangerous electrical shocks. The National Electrical Code, or NEC, requires that subpanels be bonded to the grounding electrode, not to the neutral bus. Bonding a subpanel to the neutral bus violates NEC Article 250.24 A1, which prohibits bonding the neutral conductor to any non-current carrying metal enclosure or equipment. Furthermore, there are other hazards to consider. 1. Reduced system reliability. A ground loop can interfere with the proper operation of ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or RFCIs, reducing the system's ability to protect against electrical hazards. 2. Corrosion and pitting can occur. The flow of stray currents through the neutral conductor can lead to pitting and corrosion of the conductor and its connections, increasing the risk of circuit failures. 3. Equipment damage can occur. Overvoltage conditions caused by bonding a subpanel to the neutral can damage sensitive electronic equipment connected to the subpanel. The integrity of the grounding system is paramount for electrical safety. Grounding ensures a low impedance path for fault current to return to the source, facilitating the quick operation of overcurrent protective devices like circuit breakers and fuses. This rapid response minimizes the duration of a fault, reducing the risk of electrical shock and equipment damage. Impedance is the total opposition to current flow in an alternating current circuit. It is similar to resistance in a direct current circuit, but it also takes into account the effects of capacitance and inductance. Low impedance is crucial in a grounding system to allow for a large fault current to flow quickly, tripping the overcurrent protection and clearing the fault. Ground loops can introduce unwanted impedance into the grounding system. When a subpanel is improperly bonded to the neutral, it can create an alternative path for current flow. This alternative path may have higher impedance than the intended grounding path, impeding the flow of fault current and slowing down the response of overcurrent protective devices. A high impedance ground loop can prevent a ground fault from being cleared quickly, increasing the risk of electrical shock. Furthermore, stray currents flowing through the ground loop can cause electromagnetic interference, or EMI, which can disrupt the operation of sensitive electronic equipment. Voltage imbalance refers to unequal voltage levels between the phases of a three-phase electrical system or between the neutral and each phase in a single-phase system. In a balanced system, the voltage should be equal across all phases. However, imbalances can occur due to various factors, including uneven loading, faulty equipment, or improper grounding. When a subpanel is improperly bonded to the neutral, it can contribute to voltage imbalances in the electrical system. This is because the neutral conductor can become a path for current flow between different parts of the system, leading to voltage drops and variations. Voltage imbalances can cause several problems, including reduced equipment performance, increased energy consumption, and premature failure of electrical components. Motors, in particular, are susceptible to damage from voltage imbalances, as they can cause overheating and reduced torque. Overheating occurs when the temperature of an electrical component exceeds its rated limit. This can be caused by excessive current flow, poor ventilation, or high ambient temperatures. Overheating can damage insulation, melt conductors, and ultimately lead to equipment failure. Bonding a subpanel to the neutral can increase the risk of overheating because it can create a path for stray currents to flow through the neutral conductor. These stray currents can generate heat, especially in undersized or poorly connected neutral conductors. Overheating can also occur if the subpanel is overloaded, meaning that it is drawing more current than it is designed to handle. This can cause the neutral conductor to become excessively hot, potentially leading to a fire. Fire hazards are a serious concern in electrical systems. Electrical fires can be caused by a variety of factors, including short circuits, overloaded circuits, loose connections, and damaged insulation. Bonding a subpanel to the neutral can increase the risk of electrical fires by creating a path for stray currents and increasing the likelihood of overheating. In addition, improper grounding can prevent overcurrent protective devices from operating correctly, allowing fault currents to persist and potentially ignite nearby combustible materials. Electrical shock is a potentially fatal hazard that can occur when a person comes into contact with an energized conductor. The severity of an electrical shock depends on several factors, including the voltage of the electricity, the amount of current flowing through the body, and the duration of the contact. Bonding a subpanel to the neutral can increase the risk of electrical shock by creating a ground loop. A ground loop can provide a path for current to flow from the subpanel enclosure to other conductive surfaces, such as water pipes or metal equipment. If a person touches one of these conductive surfaces while also touching an energized conductor, they can receive an electrical shock. National Electrical Code, Article 250 provides comprehensive requirements for grounding and bonding electrical systems to ensure safety and prevent electrical hazards. The NEC specifies that subpanels must be grounded to the grounding electrode system and that the neutral conductor must be isolated from the subpanel enclosure. NEC 250.24 A1 specifically prohibits bonding the neutral conductor to any non-current carrying metal enclosure or equipment on the load side of the service disconnecting means. This requirement is intended to prevent ground loops and ensure that fault current flows through the grounding conductor, not the neutral conductor. Ground fault circuit interrupters, or GFCIs, are designed to protect against electrical shock by detecting small imbalances in current flow. A GFCI constantly monitors the current flowing through the hot and neutral conductors of a circuit. If there is a difference of more than a few milliamperes between the two currents, the GFCI will trip, interrupting the circuit and preventing electrical shock. Arc fault circuit interrupters, or RFCIs, are designed to protect against electrical fires by detecting arc faults. An arc fault is an unintentional electrical discharge that can occur when there is a break in a conductor or insulation. RFCIs can detect these arc faults and trip the circuit, preventing the arc from igniting nearby combustible materials. Corrosion is the deterioration of a material due to chemical reactions with its environment. In electrical systems, corrosion can occur on conductors, connectors, and enclosures. Corrosion can increase the resistance of electrical connections, leading to overheating and potential failures. Bonding a subpanel to the neutral can increase the risk of corrosion because it can create a path for stray currents to flow through the neutral conductor. These stray currents can accelerate the corrosion process, especially in areas where there is moisture or other corrosive substances. Equipment damage can occur as a result of various electrical hazards, including overvoltage, undervoltage, transients, and harmonics. Overvoltage occurs when the voltage in a circuit exceeds its rated limit. Overvoltage can damage sensitive electronic equipment such as computers, televisions, and appliances. Undervoltage occurs when the voltage in a circuit drops below its rated limit. Undervoltage can cause equipment to malfunction or fail prematurely. Transients are short-duration voltage spikes that can occur due to lightning strikes, switching operations, or other disturbances. Transients can damage electronic equipment and disrupt its operation. Harmonics are distortions in the sinusoidal waveform of alternating current. Harmonics can cause overheating, reduce equipment efficiency, and interfere with the operation of sensitive electronic equipment. In addition to the specific hazards mentioned, there are other potential risks associated with improper subpanel bonding. These risks include increased electromagnetic interference, or EMI, which can disrupt the operation of sensitive electronic equipment. EMI is a disturbance caused by electromagnetic radiation that can interfere with the operation of electronic devices. Improper grounding and bonding can create conditions that generate EMI. Another risk is accelerated wear and tear on electrical components. Stray currents and voltage imbalances can accelerate the wear and tear on electrical components, reducing their lifespan and increasing the risk of failure. Additionally, there is increased potential for nuisance tripping of circuit breakers. Nuisance tripping refers to the unexpected and unwanted tripping of circuit breakers. Improper grounding and bonding can create conditions that cause circuit breakers to trip unnecessarily. Correct subpanel bonding is essential for electrical safety. Ensure the subpanel is properly grounded to the grounding electrode system. The grounding electrode system typically consists of a ground rod, metal water pipe, or concrete encased electrode. Isolate the neutral conductor from the subpanel enclosure. The neutral conductor should be insulated and kept separate from the metal enclosure of the subpanel. Use a separate grounding conductor to connect the subpanel enclosure to the grounding electrode system. The grounding conductor should be sized appropriately for the size of the subpanel service conductors. Verify that all connections are tight and secure. Loose connections can create resistance and increase the risk of overheating. Regularly inspect the subpanel and grounding system for signs of corrosion or damage. Address any issues promptly to prevent potential hazards. Adhering to the National Electrical Code is critical for safe electrical installations. The NEC provides detailed requirements for grounding and bonding electrical systems. Consult the latest edition of the NEC and follow all applicable requirements. Understanding the potential hazards associated with improper subpanel bonding is crucial for electrical safety. By following proper grounding and bonding techniques and adhering to the National Electrical Code, you can minimize the risk of electrical shock, fire, and equipment damage. Remember to always consult with a qualified electrician for any electrical work to ensure that it is done safely and correctly. Understanding electrical concepts such as impedance, voltage imbalance, and harmonics is essential for troubleshooting and maintaining electrical systems. Consider taking electrical training courses to enhance your knowledge and skills. Regular inspection and maintenance of electrical systems can help to identify and address potential problems before they become serious hazards. Develop a routine maintenance schedule for your electrical system and follow it diligently. By taking these precautions, you can ensure the safety and reliability of your electrical system. Always prioritize safety when working with electricity. If you are not comfortable performing electrical work, hire a qualified electrician to do it for you. Electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Stay informed about electrical safety best practices. The Electrical Safety Foundation International, or ESFI, and other organizations provide valuable resources and information on electrical safety. Take advantage of these resources to stay up to date on the latest safety recommendations. Remember that electrical safety is an ongoing process. By staying informed, following best practices, and taking precautions, you can help to prevent electrical accidents and ensure the safety of your home or workplace.